So now we're going to have a brief discussion about where the water comes from. So the origins of the ocean's water go all the way back to the beginning of the universe and the Big Bang. When the universe formed about 15 billion years ago, it was made primarily of hydrogen and helium. Hydrogen 75% and helium 25%. Now you'll notice you can't make water with that. Water, you need oxygen. Water is H2O. So we have the hydrogen, but we need the water. So where do we get the water? Well, we get the water from stars. Stars condense from hydrogen and helium gas, and they collapse and begin to rotate. And we'll take a little look at the next slide on exactly how stars and planets form. We'll see the protostar and the disk. But what you need to know at this point for creating water is how a star works. So once that nebula forms, and it forms through the condensation of these gases. So essentially the gases are forming little drops of liquid and little bits of ice. Once that material forms, if the mass is big enough, it will start to collapse. And as it collapses, what that means is all the mass is collecting in primarily in the center of this system that's forming, and it will form what we would call a star. So as this nebula collapses and forms a star is officially born when the density of the material is high enough and the gravity is strong enough to force hydrogen atoms into each other. Their nuclei combine and create helium, and this is hydrogen fusion. So if we were to look at our sun, which is a star, at the core of our sun, hydrogen is fusing to create helium. If you get a big enough star, the helium can then fuse to make larger atoms. And this fusion can create elements all the way up to iron, which is really not that big of a nucleus, but it's still pretty big. So, so that's what's happening in the core of a star. Most stars are just making helium. However, at the end of their life, what's happening in the core of a star is a sort of a balancing act. The fusion reaction produces a lot of energy, which pushes back out. So the reason the star doesn't completely collapse is because the fusion's energy is pushing out while the gravity is pushing in. Near the end of a star's life, it begins to run out of hydrogen fuel. It's basically fused most of the hydrogen at the core into helium, and so the reaction slows down. And when that reaction slows down, then the pressure out, the pressure that holds that star and prevents it from collapsing, diminishes, and the star begins to collapse further. And this is going to lead to the end of the star ultimately. When that collapse begins to occur, fusion kind of ramps up, and elements that are larger than iron can then begin to fuse, and eventually the star will go nova or supernova, in which it completely explodes. So that reaction, balancing off the gravity, completely falls apart. The star completely collapses. Very large elements are fused at the core of this nova supernova event, but at the same time, the star gets blown apart, so those larger elements get cast out into space. And so that ultimately is what leads to the next generation of stellar nebula, which instead of being limited to only hydrogen and helium, now have other elements present, including oxygen. And the oxygens and hydrogens can then get together and make water. So really the source ultimately of the ocean's water is hydrogen from the origin of the universe, plus oxygen and all those other dissolved elements that we find in seawater from the ultimate collapse of these stars into novas and supernovas, which then spread that material back out into space and again, provide for the next generation of stars. So our solar system is probably a second, third, or fourth generation star system. And that's why we have these larger elements that allow us to have not only water, but all the dissolved materials in the ocean, as well as all the elements that make up the land and the material that makes up the solid planet itself. So let's take a closer look at the origin of our ocean. So here is our planetary accretion model. We already mentioned on the previous slide the condensation that forms the nebula. And as the nebula collapses under its own gravity and begins to rotate, that combination of collapse and rotation creates a protostar and a surrounding disk. So we can see the protostar here in the middle. We can see the disk rotating around it. And the material in the disk has gravity as well. And so as this material condenses, it forms little chunks and pieces. Those little chunks and pieces run into each other and stick together in some cases. That larger piece now has a little bit more mass and a little bit more gravity. It's able to attract more material. And so you see the disk kind of dividing up into different sections. Each section ultimately will become a planet. So if we look at exactly how a planet forms, there's a couple of ideas of how this could occur. As this system is forming and the stars being ignited at the middle, depending on where you are in the disk and the temperature and the composition, you can make different types of planets. So some planets will be made mostly of hydrogen and helium. That would be in our solar system like Jupiter and Saturn, and some of them are what we call the rocky planets. In our solar system, they're closer to the sun because the temperatures and compositions and things are correct to form those rocky planets. We get some larger elements condensing, and as they condense, one of two pathways seems to be followed, or maybe it could be a mix of the two. The homogeneous accretion model, which is listed first here, is the one that they show you in the book, where basically everything in that section of the cloud kind of gets attracted together, and you get a planet that has a sort of a homogeneous composition throughout. So what you find in the middle would be basically the composition you would find near the outside. Now we know that our planet actually looks like the picture down at the bottom here. Our planet is layered, and those layers are compositional and density layers. We have iron and nickel at the middle, and we have lighter and lighter elements as you move farther and farther out until you get to the outermost layer, which is what we're interested in, which is made of water and gas. So basically the atmosphere and the ocean are the two outermost layers on the planet. So how do you get from accretion to a layered planet? Well, the homogeneous model says after everything collects, the heat of putting all that stuff together plus radioactivity melts this material. Once it's melted, the heavy stuff or the dense material sinks to the middle. The light material moves to the outside, and you end up with a layered planet. The other model, which is labeled heterogeneous accretion, says something a little different goes on here. It says early on in this process, the elements that are available are going to be the heavier elements. So you're basically going to collect your initial planet and make it out of the heavier elements that end up in the core. In our case, it would be iron and nickel. And then as the process goes on and this whole system kind of cools off, lighter elements can condense, and then they can collect and make the next layer and the next layer out. In this model, you don't add the ocean and the atmosphere until the end. One of the appeals of this model is that we know from looking at other planets and the moon that the solar system had some very heavy bombardment early on, including very large objects that would have struck the Earth. And those impacts would have been enough to heat things up and drive off any atmosphere that had come from the interior of the planet. So you would have to then rebuild that atmosphere multiple times. With the heterogeneous accretion, that's relatively easy to do because you keep adding more comets and they keep adding to the atmosphere at the end. There's also a combination model that says as you accrete things, you're not accreting distinct layers, but you're also not accreting a homogeneous body. Instead, you're doing a little bit of both. So there's already some differences between the layers, and when we get to the molten stage, the separation can happen a little bit quicker that way. And then at the end, you can keep adding more atmosphere even if it occasionally gets blown away. The end result, though, is that we do get a layered planet. One of the questions for us when we look at the ocean is, are the ocean and atmosphere still being added to by comets? Because heterogeneous accretion would say, yeah, you're probably still adding some more material even at this late stage in the planet's history. This would have all happened around 4.5 billion years ago. So a long time has passed since then. But the heterogeneous model suggests that we're still adding material. Homogeneous model, probably not so much. And so we actually kind of look, are we still adding material from comets? The answer is yes. There is a question as to how much and how significant that is. So the source of the ocean, under the homogeneous model, primarily outgassing from the planet's interior as it separates. Under the heterogeneous model, it's primarily from comets crashing in. And what's more likely is it's probably a little bit of both. One of these may be more important than the other, but we see pretty good evidence that both of these are occurring, that we are, or at least initially, added quite a bit of ocean material from outgassing, but also quite a bit from comets as well. And then, once you get past that 4.5 billion year mark and you kind of put the planet together, then what happens? Well, during the first 500 million years or so, the planet is cooling. The water is in the atmosphere, but it's still a gas. And the planet needs to cool in order for that water to condense and form oceans. And the liquid oceans that we have been around for at least 3.5 to 4 billion years. So they've been around for a long time. But again, the planet had to cool for that to occur. And then once you have that liquid ocean along with the atmosphere, it has been modified significantly by life and by chemical processes. Some of the significant changes have been the sequestration of carbon dioxide and some other elements that we'll talk about later on in the semester. One of the notable ones would be early in the ocean's history, there was probably a lot of dissolved iron. But once oxygen gets added to the ocean and the atmosphere, that iron forms a solid molecule when it combines with oxygen and then settles out and is taken out of the system. Carbon dioxide is sequestered by living organisms as well as by chemical reactions, and that gets us to the ocean that we have today. So to wrap this up, why do we have an ocean of liquid water? We look around the solar system. Other planets do not. And one of the big reasons, of course, is the composition. You have to have the right composition. It turns out you also have to have the right planet size and gravity. If the gravity is too high or too low, you're not going to get liquid water, or if it's too low, you're not even going to retain it. It will vaporize, and that appears to be what has happened on Mars. We're at the right distance from the sun. We get the right amount of energy from the sun. We're not too hot, and we're not too cold. And if you think about it, if we get just a little bit colder, the planet freezes. There's evidence that we've had a snowball Earth a few times in the distant geologic past. If you're too close, everything vaporizes because it's too hot. And the shape of the orbit has to do with that as well. And life on the planet, it turns out, gives some feedbacks that keeps us at the right temperature to maintain liquid water.